Alright, chemistry students, we are beginning video 4.1a, which is talking about the arrangement of electrons in atoms. And during this chapter, we're going to figure out why we see the colors that we see. So we are going to discuss the spectrum of colors viewed and really how electrons play a role in viewing those colors. I'd like to watch a short video clip to discuss a little more about color.
Whether we think about it or not, chemistry has always played a big role in art and culture. Just take colors, for example. But what is a color really? And what led to the use of some colors in the first place? Let's trace a color back to its roots and leaves.
Well, one color story started with this plant called Indigofera tinctoria, or indigo. It's native to India, and the name comes from the Greek word indikon, meaning Indian substance. Substance? Well, in this plant, there's a colorless molecule that looks like this. But under some conditions, this molecule can react and change, looking like this instead. So, what's the big deal then, you say? Well, in chemistry, rearranging the molecular structure like this can be like night and day, or in this case, like green and blue, because this last molecule is blue. After its discovery, people now wanted the blue indigo molecule, especially for dyeing clothes. But this is where it gets a little tricky. You see, this blue indigo molecule is insoluble, meaning the blue dye simply won't stick. We now know that to overcome this, the solution the dye is in has to have a high pH. Well, people did still figure this out a long time ago. So what did people have a few thousand years ago to raise the pH? Well, did you know that urine becomes basic over time? What is believed to have happened is that leaves from the indigo plant got accidentally soaked in urine. So if a textile came in contact with a basic urine indigo solution, it turned blue. So the high pH actually helped the molecule stick to the fabric. But wait a minute. How can this molecule be colorless and this be blue? Hey Luis, can you take it from here?
On it! Alright, when we look at the two molecules again, we can see that the blue molecule is larger and has a greater number of double and single bonds. It is this molecular structure that ultimately makes us see the colors. But first, we need light. Light contains wavelengths of all colors. If something is black, all the colors from the light are absorbed and none is reflected back to our eyes. And we therefore see the object as black. Now if we look at something colorful, we see the red color because the flower reflects back the red wavelengths and absorbs others. And the reason the flower absorbs particular colors comes down to its chemical structures.
So as stated in the video, white light is light that is completely reflected off the object that we are seeing. It is not going to be absorbed by that surface. In the video, it also mentioned about individual colors. You are going to see those individual colors when a surface absorbs the light rays that strike it, except for the color of the wavelength that the surface is reflecting back into your eye. So think about the Roy G. Biv here, and as the red poinsettia gives off the red light to us, that's because it's absorbing all the other colors of the spectrum. Now let's go back to the video to find out a little more about the colors that we see.
So these alternating double and single bonds are the reason the indigo molecule is blue. And if certain atoms are added to the molecule, the absorbed wavelengths can change. And that makes us see a different color.
The discovery of indigo color was huge for ancient art and culture. And by understanding the chemistry behind it, we can now synthesize the same molecule that was for so long extracted from this plant. And the use of indigo is still booming. In fact, we use about 13,000 metric tons every year. And if we weren't synthesizing the molecule, we would have needed about 3.9 billion kilograms of plants per year. And by the way, you might even be wearing some of it right now.
So we've learned that the colors that have an important role in art and culture have some interesting chemistry histories to tell. And the reason we see colors in the first place comes down to the structure of the molecules. And just by changing the molecular structure slightly, we can even change the color we see. And here's a challenge. Can you think of any other colors that have come from plants or animals? And remember, chemistry is all around you.
So as stated in the video, when we're talking about light, a surface is absorbing the light and it produces a certain color. Now the reason that exists is because we have light behaving as a particle and a wave. That is the electromagnetic spectrum. And here we see our Roy G. Biv. So red all the way down to violet. And we're actually increasing in energy from red to violet, where red has a longer wavelength, so it is moving a little slower, and violet is moving really, really fast up and down as a wave. But we also have to understand that light behaves as a particle as well, so we can view it as a small little electron almost, some type of particle that when it strikes the surface can bounce back into your eye. Now, how electrons play into this. Electrons, we know they are in a orbital around the nucleus of an atom. And there's two places where you can find an electron. The first place you can find an electron is at its ground state. That is the lowest energy level that it exists in. When a photon comes in and strikes an electron at its ground state, it can become excited, so it gains energy. And the electron actually jumps up to an excited state, which is an electron in a higher energy level. Now this is important to write these definitions down as we're going to look at an example of this. So what am I really talking about when a photon of light, so a particle of light, is absorbed or emitted by an atom and its electrons? So the diagram here depicts an electron, or a photon, coming in to an atom. So as a wave, it is a particle in a wave, that is the electromagnetic spectrum there. The photon will strike this electron. The electron gets excited and jumps up to a higher energy level. That is absorption. The electron is now in its excited state. However, it cannot stay there because it's not typically found there. So it will fall back down to a less excited state. When it does that, it gives off a new wave of light. And we can measure the frequency of this, or the energy of this wave that is given off as the electron drops back down to its ground state. And we can determine, based on the color of the spectrum here, so our Roy G. Biv, what color of light that is going to be that's given off. The main points here that you need to take from this is that the model here is based on Bohr's model of the atom, where the electrons are in orbits around the atom. Understanding that we now understand they're in orbitals, but the same concept applies. Light comes in, excites the electron, it jumps up, and it falls back down. So that is our absorption and emission of photons. For an electron to reach the excited state, it must absorb a minimum amount of energy. This is important to know. That is the quantum energy that the electron must absorb. And the further an electron is from the nucleus, the more energy it has. So the higher it jumps, the more energy it has. Again, one final look here at this diagram shows an electron that's here. Energy will come in, excite the electron. It stays in the excited state and drops back down and gives off light. And that light we see is of a certain frequency, which makes it of a certain color.